x-plane and Moiv's theorem. So this is called the complex plane. Instead of x and y, it has x and I.
Why are you on the other side?
Okay? Give me that.
They won't punch
Thank
it
you.
on the wrong
Okay?
side.
Instead of x, what?
Why are you, why is this?
Because they will punch it on the wrong side.
Why is this what?
It was confusing.
Oh, did I punch it on the wrong side? Sorry. Okay. So in the complex plane, you have this direction is the x direction and this direction is the I direction. So there are useful applications of plotting points in the complex plane for solving equations that involve, for solving systems that involve complex numbers and stuff like that. So if I were going to graph a point in the complex plane, say like a complex or I would like say you have a number like 3 minus 2i. To graph that point, it's just like this is x and this is y. So to graph that point, I would go over 3 in the x direction and down 2 in the I direction. And that's how you graph that point. Got a complex number is a number of the form z equals a plus bi, and this is called the real part, and this is called the imaginary part. So if you have a pure imaginary number like 3i, just plain 3i, and I want to graph that, that would be 0x plus 1, 2, 3i. That point would be like over there. All right? So, and the absolute value of a number is the distance. The absolute value of a number is the distance from 0 from the origin. Well, yeah, we're getting to that. So this thing means the complex, this is the conjugate of a complex number. And so for instance, if my complex number is 3 minus 2i, its conjugate would be 3 plus 2i. And if you remember about conjugates, the conjugate, when I multiply those conjugates together, it turns it into a real number. Because when I multiply this times this, I get 9. And what happens to this times this and this times this? Those two things cancel each other out, right? Negative 6i and positive 6i cancel each other out. And then I get minus 4i squared, which gives me 9 minus 4 times, and I squared is negative 1. So you get a real number, which is equal to 13. Okay? So when you multiply a complex number by its conjugate, and this little bar on top means conjugate, you get a real number. If I take the square root of that real number, that gives me the magnitude or the modulus of that complex number. And it also represents the radius of that point if I were going to graph it in polar coordinates. So if I wanted to graph, if this is my point 3 minus 2i, this segment, this radius, would have a length of square root of 13. Okay? And you could find that either by taking the complex number times its conjugate and taking the square root of that, or by taking the a part and the b part, squaring each of those, and then taking the square root of that. That gives you exactly the same thing. Get that? Yes? No? All right. Again, just like with in polar coordinates, can I move down? I guess I could go down. Okay. So just like in polar coordinates, the argument is the angle that that complex number makes with the positive x-axis. But again, you have to pay attention to which quadrant that should say theta is in. Does that say theta on your paper?
No.
No. Pay attention to which quadrant theta is in to find the angle. And we'll talk about that down here in a minute. Okay? Polar form of a complex number looks like this. Z equals x plus yi. R cosine theta plus r sine theta I. So this actually gives you x, just like it does with polar coordinates. And this gives you y, just like it does with polar coordinates. You could pull that r outside. And sometimes this is known as r cis. Okay? But I don't think this is in your book, so you don't really have to worry about that. We're not going to worry about that. Okay? So plot the point corresponding in the complex by and write it in polar form. So you'll see some problems that look like this. So you go out root of 3, which is about 1.732. And then you go down how much? 1. So you would go down like that. So that's this point right there. Now to write it in polar form, first thing you have to do is find r. So r is the square root of 3 squared plus -1 quantity squared, which gives you 2, right? That's the square root of 3 plus 1, which is equal to 2. Okay? So that's r. But you have to find theta, okay? And so if you take the inverse tangent, there. So if you take the inverse tangent of -1 over root of 3, you should get theta unless it's in this quadrant, in which case you'd have to add 180 to it, okay? So this is equal to the inverse tangent. If I rationalize, multiply by root of 3 over root of 3, I get negative root of 3 over 3. Does anyone remember what the inverse tangent of negative root of 3 over 3 is? It's either 30 or 60. Yes, again.
30.
Yes, it's 30. Okay. So this is negative 30 degrees. Okay, or negative pi over 6 radians. And sometimes they'll say express it in radians. This doesn't specify, so we're just going to put it in degrees. So to write this point in polar form, I would write it as 2, because that's our cosine of, you have to put parentheses like this, 2 cosine of negative 30 degrees plus, they usually put the I in front, I sine of negative 30 degrees. And that's it, okay? Did I do that right? I think I did. Questions? Nathaniel?
Is R cis too much to like R bro?
Is our cis like our bro? I get it.
Yeah, that came out wrong.
Yeah. Right. Our
What
cis.
did you do last session?
Huh?
What did you do in the last session? Like 2 cosine negative 30?
This? Oh, there should be another print. Because this is r, which I pulled out here, right? Cosine of theta, which is negative 30, right? Sine of I sine. I'm just plugging into this formula right there.
Okay.
I sine of negative 30.
And are you going to solve that?
No, I'm done. Okay, it just writes in polar form. Now, if I had used the angle 330 positive, that would give me exactly the same thing, right? And so I could have used 330 as well, because both of those will get you, the cosine of that is the same, right? Cosine and the sine is the same. 330 is the same, will get you to the same spot. So in other words, I could have gotten to this point by going over 2 and then rotating through an angle of negative 30 degrees, where that angle would be 30. You understand? It's just like polar coordinates, except you're talking about the I direction instead of the Y direction. Next. So now, if you're doing the next thing, can I erase this? Sure you can. Okay? So the next thing, plot the corresponding point on the corresponding to 2 cosine 30, I sine 30, and write it in rectangular form. So to graph this point, this means that I go over 2, so here you're going the opposite. So you're going over 2, and you're rotating through 30 degrees. So maybe something that looks like this radius is 2, and this angle is 30 degrees, and this is your point that you're talking about right there. Got? And to write it in rectangular form, all you do is you multiply this stuff out. So some of you might remember from last semester what the cosine of 30 is. Please, someone remember what the cosine of 30 is.
Root of 3 over 2.
Root of 3 over 2. You were thinking sine, so go ahead and say what the sine of 30 is, Josh.
1/2.
1/2. So times 1/2. And then you could go ahead and multiply that through, and what happens is the 2's cancel out in both cases, and you get z equals, that cancels out, root of 3 plus I over 2, right? Or, no, sorry, no over 2. No over 2, just plain old I, because the 2's cancel out. And so if I had gone over square root of 3 and up 1, I could have gotten to exactly the same point. See? Just like polar. Except then we have these weird equations. Can I erase that? Go next page? Sure, you can. So, on the next page, they have these 2 formulas. Product of complex numbers and quotient of complex numbers. And they look really, really ugly, but they're really easy to plug into. Okay? So there are applications where you might need to multiply 2 complex numbers. Like I told you, like when you're doing like wind flow or aerodynamics or finding subatomic particles or something like that. I'm not sure. I'm not an astrophysicist, but yes,
Why
sir.
is it that when they're taking the square root of a negative number, why can't they just take the absolute value of that? What's that? That's not the calculation.
I don't know. I'd be BSing you if I told you that. Okay, but I'm not going to make up stuff. So anyway, all you do is you plug into these formulas. So to find z times, so here you have 2 different complex numbers and you want to multiply them together. So you just use this formula. And this is R1 and this is R2. So z times w is just 3 times 5. That's what goes in there. 3 times 5. Cosine of 20, you add the angles. So if it's multiplication, you add these 2 angles together. And so you get cosine of 120 plus I sine of 120. And what's nice is that theta is going to be always be the same for both sine and cosine, right? And then you multiply, you try to simplify it as much as you can. Like if they say leave in polar form, then you leave it like that. If they say write your answer in rectangular form or standard form like this, then you try to multiply things out. So cosine of 120, anyone remember what that is?
1/2.
Negative 1/2. Okay? And sine of 120, anyone remember what that is?
Root of 3 over 2.
Positive square root of 3 over 2. So if I wanted to simplify this in standard form, you could write it as negative 15 over 2 plus 15. I times 15 root of 3 over 2. Is that hard? No? Okay. Now if I want to find z over w, I just do the opposite thing. So I just take 3 divided by 5. I subtract the angles. So I get cosine of 20 minus 100, which is negative 80, plus I sine of negative 80. And if they ask you to find the answer to the nearest tenth, then you actually, this we don't know an exact value of. So you would actually plug that into your calculator to come up with a number. But if they say leave it in polar form, you just leave it like that. Got it? All right. We don't do Facebook during math lectures. Okay, thanks. All right, de Moivre's theorem says this. So de Moivre's theorem is apparently, it's some very famous mathematical theorem which has some applications, and there's a couple things that are pretty cool about it. So what this gives you is kind of an application of that multiplication formula up there. But if you have a complex number that you want to raise to a power, you can use de Moivre's theorem. So for instance, in this case, I want to raise this to a power of 3. And so n is the power that you're raising to it. So if I wanted to do this, this would be 2 to the third power times the cosine of 3 times 20, which is 60, plus I sine of 60. Do you guys see where I got that from? It's n times theta, and you raise this to the n power. So basically, you are multiplying by itself 3 times, really, is what you're doing. And then you can multiply this out. 8 cosine of 60 happens to be 1/2. Sine of 60 happens to be root of 3 over 2. So if I wanted to simplify that further, that's equal to 4 plus 4 root 3 over 2. I like to put the I after in that case. All right? Yes, sir.
Wait, why is it
Shouldn't it be
It's
8
just-
over root
yeah, it's
3
just 4
divided by 2?
root 3,
8 divided by 2 is 4.
but then it wouldn't be.
On the other
Oh!
one, you have that.
Yeah, I'm
you
not
have
thinking.
both.
See,
You have both.
I'm sorry. We're root 3. Thank you. Okay. Next. So this is kind of cool because if I had a number like this, say I have 1 plus I, and I want to raise it to the 5th power, okay? Traditionally, if I want to do it the long way, I would go 1 plus I times 1 plus I times 1 plus I, right? Times 1 plus I times 1 plus I, which is a pain in the neck. Because first here you're going to get a quadratic, and then you're going to multiply a quadratic by a binomial, and you're going to get a cubic, and then you're going to multiply that cubic, and you're going to get a quartic, a 4th degree, and you're going to multiply this by, and it's going to take you a long time. It'll probably take you 15 minutes to multiply that all together. But if you know de Moivre's theorem, there's kind of a shortcut to doing that. So I'm going to erase all this. And first thing you do is you write this in complex form. So first you have to find r. Can anyone tell me what r is for this complex number? What's a? 1. What's b? 1. So it's 1 plus 1 squared, square root of that, which is?
1.
No. Square root of 2 is not 1. Okay? Square root of 2. Okay? And then you have to find theta. Okay? So if I were going to graph this point, 1 plus 1i, which quadrant am I in?
First.
I'm in the first quadrant, right? So what is the inverse tangent, okay, of 1 over 1? Anyone remember what that is? Inverse tangent of 1?
45 degrees.
45 degrees, okay? So now I have this number written, 1 plus I written in complex form, can be written as z equals root of 2, root of 2 cosine 45 plus I sine of 45. But what I want to do with that is raise that whole thing to the 5th power. Okay? And I can use de Moivre's theorem to do that. Because what do I do with this root of 2? What power do I raise it to? The fifth power. So you have, so to the fifth power, this is equal to root of 2 to the fifth power. Okay? Cosine, time, big brackets, cosine of 45 times 5. Anyone know what 45 times 5 is?
45 times 5.
225.
225. How do you know that? Oh, because I wrote it as 225. Okay?
Do you multiply it by 5?
Because of de Moivre's theorem. It says if I want to raise this to the fifth power, it's this raised to the fifth power times the cosine of 45 times 5. That's what this says up here. Okay? N is 5. See that? Okay? So in this case, N is 5, and theta is 45, so I multiply that out. Now, using some quick math, what's root of 2 times root of 2? 2. So I have 2 of those, right? So root of 2 times root of 2 times root of 2 times root of 2 is 4, and I have one more root of 2 left over. You understand that? That's root of 2 to the fifth power. Cosine at 225 is an angle in the third quadrant, and that comes out to be negative root of 2 over 2. Who said that? Who said that over here? Very good, Nikki. Plus I sine of, no more sine. What's the sine of 225? I'll give you a hint. It's exactly the same thing, right? Because sine and cosine are both negative, okay? In the third quadrant. And then when I multiply, now when I do some simplification, what's root of 2 times root of 2? 2 times 4 divided by 2 is? 4. So I get 4 plus
Minus 4.
minus, minus, right? Because that becomes negative.
No.
Minus,
No,
Before the
minus
4,
four.
negative 4.
Negative 4.
yeah, negative.
No, negative 4 plus.
The 4 that you have written down
Oh, you're
is
right.
negative.
Negative 4, sorry. Minus 4i. You understand that?
Yeah.
Yes? So this is this thing raised to the fifth power. To show you that this is true, and I'm not going to let you do this on a test, okay? Watch this. Did you know you could do this on your calculator?
Erase everything at once?
What? Turn. Watch. If I go to my graphing calculator, okay? I don't think you even have to turn the eye thing on. If you just go on, whoops, where? So I could go, we were taking 1 plus I, right? 1 plus, the I is above the decimal sign. Whoops, I have to put that in parentheses, sorry. Parentheses, 1 plus I, which is above the, I shouldn't really show you this, okay? And I raise that to the fifth power, okay? I get negative 4 minus 4i, which is just, yeah, but that's doing all the algebra for you, right? So you don't want to multiply it longhand. You can do this to check, but you need to use on a test. You need to use, like, turn it into polar form, and then apply de Moivre's theorem, and then simplify it, and you end up with the same answer. Okay? Isn't that cool? It's kind of cool. All right, this last part, I'm going to save this for tomorrow, because that kind of gives people a headache.
Oh, gosh.
All right? And that's all, folks. We're going to stop recording.